and he will tell us about the Trail of Lost Pennies. Thank you, Alan.
Thank you, Adrian. Thanks, Sander, for the invitation. I'm certainly honored to speak to you today. I'll do so on a topic concerning game theory, concerning random turn games. The talk is in these 5 parts. I won't try to summarize them now. It's a kind of fascinating story, though, of a literature, a topic that has in fact had 2 rather rich but very separate lives in mathematics and economics, and I'll try to give you a sense of that history during the course of the talk. And if I just want to summarize one idea at the beginning, we'll be looking at random turn games where there are several turns to be played, in which there is a mechanism for deciding who wins the turn that, while random, the players are capable of influencing in a way that means players are forced to consider the positional importance of the gameplay at the moment. They are forced to make an evaluation of how important, in a certain sense, the present turn is relative to the ensemble of future turns that are more or less likely to take place later on in the game. But let me let the themes of the talk sort of develop directly by getting involved with them. Trail beginnings in part 1. I want to give you a single turn game, very explicit, that will be illustrative of the general game I'm considering. Okay, so I've got 2 players. I'll call them Mina and Maxine in blue and red respectively. And they will each come to a table armed with a pile of pennies drawn from their own savings. Okay, so what happens is that I'm getting just a little bit of static on the noise. I don't know if, can people hear clearly? Is it okay?
Gonzalo, I think that your microphone is open. Yeah, now.
Oh, do I need to make an adjustment?
No, you were perfectly fine. Now it's fine.
Okay. So yeah, I've got my 2 players, Mina and Maxine. The game they're going to play, called Penny Forfeit, is one in which they each come with pennies drawn from their own bank accounts, and they are each asked to stake some of those pennies. So imagine that they each physically put a certain number of their own pennies on a table, and those pennies then go into a bag, shuffled around, and one of them gets picked uniformly at random. And the pennies are marked in some way so we can tell who put them in. So if when the penny comes out that gets drawn from the bag, it's from Mina, say, in blue, has a tiny blue dot on it, say, that means that that player, Mina, will be paid $1, 100 pennies, by her opponent, Maxine. And if one of Maxine's pennies gets drawn, then it's the other way around. She receives $1 from Mina in that case, 100 pennies from Mina in that case. So you see, a player is losing money by staking pennies. They're not getting those pennies back they put in, but they are potentially winning or losing a further 100 pennies according to the outcome of who gets picked. Okay, so that's a picture that represents this game. And then the natural question to ask is, if you're being put in the position of playing this game, how many pennies would you actually choose to stake? One wouldn't want to stake 1,000 pennies, for example, because the total amount of skin in the game in some sense is 200 pennies. That is the difference between winning and losing. But neither would you want to stake 0 pennies. Your opponent could simply stake 1 penny, would win the game, and then would get 100 pennies out of you from the terminal receipt mechanism. See, so there's some sort of balance and equilibrium that is achieved somewhere in the middle there. So if we represent this now with real values, I used pennies before, but now we turn to real values. So if Maxine is staking A and Mina B, then we can represent this with this sort of graphical setup. There's a counter that starts at 0 and it will immediately move and the game will finish at either 1 or -1, with a moving to 1 representing Maxine winning, and moving to -1 representing victory for Mina. So you see, if they stake A and B, we have these stakes and these corresponding probabilities. The actual probability of the penny being drawn, so to speak, is A over A plus B for Maxine. And then in a slight change of boundary condition of terminal receipt, the winner will receive 1, and the loser 0, let's say. It was in fact -1 in the setup that I said before. So we can then write down mean as a mean receipt from the game that is given by these equations. It's in red there, it's the probability of winning minus the actual cost for her, which is her stake amount. And similarly in blue at the bottom, we have B over A plus B minus B. That is the mean amount when given stakes of A and B, you see, are actually being staked. Okay. So, okay, how much then should Maxine actually stake, and likewise Mina? Well, let's use the game theoretic notion of Nash equilibrium. It's a strategy pair, which in this case is simply, well, if we're talking about deterministic strategy pairs, at least it's simply a pair of real values representing positive real values, representing the stakes of the two players. And of course, this equilibrium concept, famous concept, is the notion that neither player would choose to unilaterally deviate from it. With knowledge of what the opponent is doing, you would not be positively motivated to deviate from your own element in the pair. So it's characterized by these conditions in terms of mean receipts, that things, well, I won't try to summarize them again here, but these are the equations that sort of represent and capture the notion of Nash equilibrium is just defined there, okay? So finding the equilibrium, very simple equations. It's a question of finding a critical point for them by differentiating, and then we get these equations represented, seen in the middle of the screen here, which have in fact two solutions. A and B could be identically 0, or they could be 1/4, 1/4. Now, 0, 0, for reasons I already mentioned, isn't an equilibrium. Essentially, I mentioned that if one player is at that, they would be, if the players were at that, one player would want to up the ante to 0 plus, as it were, figuratively, to an infinitesimal amount, and then they would just win the receipt with 0 cost. So that's not an equilibrium, but the other one is. So the unique Nash equilibrium is in fact 1/4, 1/4, which might seem to correspond to 25 cents in 25 pennies in the original formulation, although it actually corresponds in that game penny forfeit to 50 cents because the money was being transferred from one player to the other rather than having a 1-0 vector for the terminal receipt. It was a 1-1. So the answer to the question posed according to the Nash equilibrium concept, which is quite natural, is both players would bid 50 pennies, put 50 pennies of their own money in playing this game. Okay, any questions?
So, quick question. So, in this game, in principle, it could be a possibility that there was no Nash equilibrium, right? Because the state space is not compact, this type of things, or am I wrong with that? But I mean,
yes, it might be. I suppose that's right. At least going to the textbooks and looking at some of the standard theorems, it's possible they might not apply. In fact, the game has a very explicit solution. Okay. So, yeah, I haven't tended to draw, in fact, in this work I'll be discussing on abstract general theorems about the existence of Nash equilibria, because the games tended to work in a more concrete way to actually find the equilibria.
Okay, thank you.
So, okay, we can do that game again in quite a natural way. You can imagine with more general turbulent payments. I mean, there's win and lose, there's 2 players, so there's 4 parameters that are listed here, and they're indexed by M for Maxine, N for Mina, -1 and +1. That's the notion that a counter moves to the left or right and reaches this terminal side. And then it's natural to impose these boundary conditions that M-1 is less than M1. That represents the notion that Maxine regards moving to the right as the right thing to do. Victory for her is represented by doing that symmetrically with the opposite kind of inequality for Mina. She wants to play to the left. And then we can introduce, okay, those are fixed quantities that specify the game. And then I can introduce quantities that describe how the game is played in a certain sense. So M0 and N0, if the players are, as it were, playing well, if a Nash equilibrium is being followed, we can then record what Maxine's mean total receipt from the game is when it is played from location 0. Or in fact, we can specify M0 and N0 as a function of just given stakes A0 and B0, and then, okay, in a special case, that may be a Nash equilibrium. So then we have equations that are very similar to the ones before, representing M0 here, a victory possibility, defeat possibility, resulting outcomes, and then the subtraction of the A0 that you're just giving up and not getting back, you see. So rearranging that equation, you have the penultimate equation on the screen, and likewise you have an equation for MENA. So, okay. In fact, at the Nash equilibrium, we can characterize the Nash equilibrium for this simple game with these boundary conditions by some equations, the ABMN equations. So A0, B0, positive real numbers in the components, that's a Nash equilibrium if the 4 vector comprised of those alongside the mean receipts from 0, M0 and A0 satisfies 4 equations, the first 2 of which are simple Markov considerations that, well, they've already in fact been recorded on the previous slide. And then there's equations that actually distinguish the equilibrium condition, that is this sort of consideration of being a critical point with one or other partial derivative being equal to 0. Those are optimality equations that are recorded in the 3rd and 4th line among those equations. So in fact, there's a unique positive solution, which is the Nash equilibrium, in which I record at the bottom of the screen capital M and capital N. These are how much skin the respective players have in the game. How much difference does it make to Maxine, a difference between winning and losing? That's what capital M is. And likewise, capital N, the difference for MENA, where naturally these are positive quantities reflected by the fact that N minus 1 is bigger than N1 at the bottom of the screen. So yes, it's that's the unique positive solution, these equations. So in a sense, we've solved that game, and now I want to generalize it into a multi-turn game, and I'll begin with a further step. Deuce forfeit. I'm drawing on the language of tennis here for this game. The counter begins at the origin, and the boundary vertices 2 out either way are the terminal locations. And then you see I have the 4 pieces of data that specify the boundary condition, the win and lose receipts for the 2 players that are indicated there in red and blue in the middle of the screen. So this is kind of like the deuce situation in tennis. If our Maxine wins 1 turn, it will become her advantage. The counter will move to 1. And if she can then close out the game by moving the counter to 2, it will finish. Likewise, advantage MENA is her winning a turn and the counter moving to -1. So at any given turn, we simply replicate the situation of the penny forfeit game. Players will stake continuous amounts drawn from their own bank accounts, and then a coin will be flipped with the probabilities determined by those stakes, as it was for the 1-turn game. So a whole sequence, potentially arbitrarily long, of turns will take place. Money will be given up by both players at each turn, and neither player will get any of that money back, neither during the game nor at the end of it, but they will get the terminal receipts as indicated by the amounts on screen here, okay? So time invariant Nash equilibrium, there's a concept that could also be called Markov perfect Nash equilibrium. This is like the concept of a Markov chain in a sense. If I tell you the information the counter is at a certain location I in open play, in this game either -1, 0, or 1, this is the notion that the player will decide how to play next based purely on the information of where the counter is now, rather than on information about the more detailed history of how the counter arrived in that location. So it's like the Markov property. In some sense, it's a completely natural property. It raises the question whether every Nash equilibrium has this additional property. I believe that is the case, although that isn't actually going to be the direction I take with this talk. And in fact, in general, I don't know the answer to that. So anyway, we can describe a time invariant Nash equilibrium. Then we can characterize the behavior of the players by the quantities AI and BI, the stakes offered by Maxine and MENA respectively, at all the locations in open play in this game, -1, 0, or 1. So in that sense, by 6 real quantities, positive real quantities, at least for a deterministic Nash equilibrium. So that's summarized here. We've got the boundary data, we've got these stakes, and then I can introduce, correspondingly to before, the mean receipts, assuming that we actually begin the game at these locations. in that way, the game is actually being summarized by, I think, 12 parameters, 4 attached to each site. The 2 stake amounts and the mean receipts they will receive if gameplay begins there and the rest of the game takes place from that location. So 12 parameters specify a time invariant strategy pair in Juice Forfeit, this new game. Now, in terms of boundary data, okay, as I've explained, that's really a 4-dimensional space of real, positive real numbers satisfied to constraints. So it's a region in 4-dimensional space. It has 4 parameters, but in fact, there's only really 1 parameter. And that is because there are some simple symmetries involved in the problem. It doesn't make any difference in terms of the mathematics of the game. It might slightly change the psychology, but not the mathematics. If I give or take away from any player a deterministic amount before the game starts. So I can simply give to the players the negative of their terminal receipts if they lose. And in that way, I can just ensure that the losing terminal receipts for the 2 players are equal to 1. If I do that, all is left is the 2 winning receipts. And then I can just do a currency valuation to ensure that one of those, a given one of those, is equal to 1. And I'll do that by saying that Maxine's winning receipt is in fact equal to 1. Just by scaling, I do that. And so that means there's only 1 parameter left that's actively describing the game. And that is what Mina's winning receipt is. That's called X here. And X is a quantity between 0 and infinity, you see. So we've got a 1-dimensional family of games in that sense for Juice Forfeit. So, all right, if we look then at the time invariant Nash equilibria, the Markov perfect Nash equilibria in Juice Forfeit, what I've got here then is this concatenation of 1-step penny forfeit games in which there are these 6, collectively A or B, 6 values forming a Nash equilibrium. And they have to solve, in fact, it's not difficult to solve, to see that they have to solve an analog of the ABM equations we saw for penny forfeit, the 1-turn game. These are basically the same equations we saw, but recorded for each site. So sort of 1-step Markov considerations and local optimality conditions are being recorded for each site to get me to a situation where I have 12 equations and 12 unknowns. So you might think in principle there would be 1 solution or a bounded number of solutions on that basis. But how do we solve the equations? So when I was getting into this work, I decided to try to find solutions by considering a more symmetric case. So I took Mina's winning receipt to be equal to 1, making it the same as Maxine's. So in that way, I then also hoped for a symmetric solution. So I then speculated there would be a solution in which the players would stake the same in the middle, and then the player whose advantage it is would be staking the same as symmetrically over on the other side when the other player had an advantage. That's represented by A1 is B minus 1. What Maxine stakes when it's advantage Maxine is what Mina stakes when it's advantage Mina, and likewise the other way around. And then I also speculated that that would lead to an outcome in which the mean receipts, when the counter begins in one of the 3 given locations, would either be equal in the middle or satisfy the natural symmetry, natural flip symmetry in the other cases. So 6 variables then remain, in fact, after those identifications are made. The AI and MI, for example, when I is in one of the 3 open play locations. So they satisfy certain equations. These are reduced from the previous ones. Perhaps it's roughly plausible. They look like this. I obviously don't expect you to absorb it in its entirety. There's in fact a unique positive solution you can solve for that's represented in fractions and decimals here, and perhaps a pictorial description is easier to absorb. For the stakes made, you see relatively big stakes in the middle of 18 cents. This is for $1 versus 0 win or loss. So there's sort of $1 at stake for both players. So getting 18 cents in the middle. And then when it goes over to be on the right advantage Maxine, she's staking much less, 6 cents. But then her opponent who's losing provisionally, Mina, is staking even less than that, 3 cents. And then you see symmetrically the thing on the other side. And then lower down, you see what the mean receipt for Mina is. So you see in the middle, she's not making that much, given the potential winnings in the games. And that does go up, but still significantly less than 1 when it's her advantage, and almost nothing when it's her disadvantage. But it is positive. Okay. So then the phrases that summarize this are here for use forfeit: competitive and equal 18-cent stakes in the middle, small stakes for Maxine when it's her advantage, but very small for Mina. And then that's naturally flipped under role reversal over on the left. Okay, so some themes sort of emerge from that to some extent. Okay. So the trail of lost pennies on a finite trail, you can probably imagine, can be defined in a more general way. There's a parity consideration if I take a finite integer interval as the game board, according to whether I have it going from -k to +k or to +k plus 1. But in any case, I can set boundary conditions, the same symmetry considerations apply. It's a one parameter family of games parameterized by Mina's winning receipt, x in 0, 1. That notation is maintained. And in fact, we can even play on an infinite trail z with boundary data that, formally speaking, represents the notion of the game finishing when the counter reaches +infinity or -infinity. Of course, we have to make sense of what that means. The counter is said to reach +infinity if the counter location, the capital X process, has a limit infimum equal to infinity. So a relatively strong definition of reaching +infinity, symmetrically reaching -infinity, and then these payments that you expect from the boundary data, and I hope the notation, are being made to the two players. Okay, and in fact, the trail of lost pennies on Z was the principal focus of the work I did. But its relationship to the finite games is important. Okay, so I want to summarize, reaching the end of this first section of the talk. I want to pose, I think, 3 broad questions or topics that are sort of raised by these games we've considered. In 2 simple examples, I've indicated that there is a precise correspondence between the time invariant Nash equilibria, essentially the equilibria in the problem, and the ABMN equations that we saw in their solutions. That is a correspondence in the cases we've seen. Pose the question, is that correspondence likewise valid for any finite trail, or indeed when we play the game in the infinite setting, with the integers being the game board? Okay, so that's one line of inquiry. And then we have this theme coming from this suggestive picture. The notion there's a lot of excitement and interest in the game, and players are prepared to stake pretty big in the middle, at the battlefield, as we can call it. But as they get away from that, we saw this rapid drop-off that was even more rapid for the player who is perceived as being disadvantaged by the movement of the counter. So that's sort of represented here. Is there a battlefield vertex with this rapid but asymmetric fall-off? As we move away from that vertex, is this true on the more lengthy finite trails? Is it true when we play on the integers? Okay, thirdly, a theme that is summarized by the phrase incentive inch, outcome mile. I want to make a highly argumentative, highly speculative, but perhaps somewhat interesting hypothesis. Consider the case where X is bigger than 1. This is a case where Mina's going to get a little bit more money when the game ends with her victory than Maxine would were it to end with hers. She's a bit more incentivized. So one might speculate on that basis that throughout the game, and it might be a long game if played on a long interval, or even infinitely many turns if played on Z, but at each turn in the game, she is perhaps just a little bit more motivated to actually play than Maxine. She perhaps stake just consistently slightly more than her opponent. But then that would create a situation in which, in fact, because of the rules of how who wins is decided, it's just be a simple, well, it would be a random walk with a constant bias. If it was a constant amount she was overbidding her opponent as a proportion Mina, then she would actually get a consistent, simple bias to the left in the game that would create a situation where the counter would predictably move as a biased random walk to the left. It would move ballistically to the left. Her victory would, in fact, be ensured if players were behaving like this. So that might then lead a Maxine to recognize that and to become discouraged. There's a discouragement effect in economics. And then Maxine might just say, what's the point of even playing this game? I'm giving up my pennies. I'm not getting them back. Maybe I should just accept the loss and then cut my losses with no running cost. But then Mina would know that. So then she could almost bid almost nothing. So it might create a situation in which even a small incentive difference for the players would create a situation where the more motivated player might win with almost no opposition. That's anyway something that, it's a hypothesis one can entertain. And that's the third theme I want to end this section of the talk with. Okay, so for Gabor, Peter, and me who are doing this kind of research, I'll explain the authorships later. But as we were getting interested in this, its origins, it came from a wave of attention to a game called tug-of-war that came from probabilist mathematicians when we were in grad school. So I wanted to tell you a bit about that in terms of this is sort of a bit of a subjective history of the topic from the speaker's point of view. So I'll start, in fact, with critical percolation on the hexagonal lattice, in which I have this fragment of the hexagonal lattice, and notice it has these boundary conditions, blue, blue, left, right, red, red, up, down, and then each hexagon is actually colored red or blue, just according to fair coin flips. And then the famous question is there a crossing in blue, left to right, or is there, in fact, in the complementary case, and it's a topological fact to do with Brown's fixed point theorem, that it is the complementary case, I think, that there's a red crossing north-south, okay? So, okay, Wendelin Werner, and giving talks, I'm sure many talks in this era about, obviously, these very exciting developments. So he would tend to mention, just an aside at the beginning of these talks, the game of hex, because people might be roughly familiar with it when he was talking about critical percolation. So this game was actually defined during the Second World War by a Dutch mathematician, Piet Hein, although it was then explored in John Nash's thesis in the late 40s. So players alternately play a hex. They call them red or blue. They put down red or blue hexagons in locations of their choosing, and then one or other wins according to whether the connection, the monochromatic connection, is forged in the relevant sense, as you see. So Wendelin asked the question at the theory group at Microsoft, in fact, could there be, I'm always giving these talks, could there be, though, a bit more of a substantial connection between critical percolation and the game of hex? So, okay, Parrish, Schramm, Sheffield and Wilson, that group in Microsoft, considered, as a result, a random turn version of hex, where each turn, a fair coin flip would decide who would win. And Maxine, as I call her, in red, would place a counter if it was heads, Mina in blue if it were tails. So under optimal play, these authors found a very nice solution to this problem, in which to basically communicate the relevant idea I want to. The played region, in fact, ultimately is played in a rather complex random order, but it is just realized and ultimately is a copy of critical percolation, in fact. Okay, so then these authors were led to introduce a very related game on a direct and in a more, well, okay, on a more graphical setting, tug-of-war, they called it. Here it is in a finite graph. Take a finite graph, distinguish certain vertices, call that the boundary, that's B, and then in green here, I've got a function, a boundary payment function defined on the boundary vertices. In other words, each boundary vertex is assigned a real value. Okay, the counter starts somewhere in open play, not at the boundary, and then fair coin flips decide each turn's victor. The turn victor gets to move the counter to an adjacent vertex of her choosing, and then to use my two players, Mina in blue will play Maxine at the end of the game, which occurs when the counter reaches the green boundary. She will pay the amount given by the evaluation of the boundary payment function f at the terminal location. So you basically run the game until it reaches a green vertex, and then Mina plays Maxine, the real number attached to that green vertex. Okay, so if the players get it right, if I can speak informally, if they play optimally, I can record h of v to be a function of the starting location in open play of the counter. Let's record the mean value of the terminal payment that gets made. There's no running costs in this game, just terminal payment. So it is not unnatural to believe that the equation written in the middle of the screen is satisfied. There is a certain average that takes place in a rather extreme form, in fact, between maximum and minimum values at the neighboring vertex, reflecting who wins the game. Maxine wants the money. She wants to move to locations where the mean amount she may expect to receive is highest. Mina correspondingly wants to minimize payment. Quite natural intuitively to believe this equation. With H restricted to the boundary condition is given naturally by the boundary payment function F. So H in this sense is a so-called discrete infinity harmonic function. Infinity harmonic is an analog of the two harmonic functions that are classical, replacing the uniform average by this max-min type average. Okay. Okay, so then to summarize the history, these players caused some interest in PDE by playing this game in a Euclidean setting. The boundary payment function is defined on the boundary of the domain. There is a small parameter epsilon. At each turn in the game, what the counter is a point inside the domain. At each turn of the game, it's 50-50 coin flip. The player who wins gets to move the counter within the green ball, whose radius is epsilon, centered on the present location. The game ends when it reaches the boundary, at which time Mina plays Maxine the real value on which the counter has alighted, the labeling by the boundary payment function. Right? Okay. So then these authors proved that the low epsilon limit of the value function of the game, or the mean amount that would be paid from one player to the other if the game is played well, so to speak, that has a low epsilon limit, which is the infinity harmonic extension of the boundary data, where the infinity harmonic extension is the solution of this PDE, again, an analog of the Laplace equation with p equals 2 in some sense to p equals infinity. If you want a slogan that roughly represents this, it's that the solution has a vanishing second derivative in the direction of its own gradient. A bit much to take in, although I'm sure some people have some familiarity already. I'm just giving you a guided tour of some of the highlights of the history. This was a theorem that's generated quite a lot of interest in the intersectional union, perhaps, of certain PDE and probability communities around 2004 to 2008, this period. So yeah, Garber Patton and I in grad school, there was a lot of interest in these games, so we wanted to get a little bit involved. So we thought we'd work with the tug-of-war game, but make the mechanism for who wins the turn a little bit more developed. It's a fair coin turn in tug-of-war, as I just described it. But state-governed tug-of-war that we considered has the following attributes. So at the beginning, both players are given budgets. Mina, for normalization, is given 1 unit. Maxine is given a quantity lambda. So at each turn, the players have in fact been spending down the initial fortunes, and an intermediate turn, halfway through the game, some of those fortunes remain. The players are then invited to stake some fraction of what remains. Stake amounts get put in, like the pennies in penny forfeit, going to the middle of the table. And then the same rule then is used to decide who wins. If the players at the turn of stake A and B, Maxine and Mina respectively, Maxine will win the turn with probability A over A plus B. And then apart from that, the rules are the same as for the tug-of-war game. The victorious player moves the counter to an adjacent vertex. We wait until it reaches the green boundary, and then the payment gets made as before according to the function F defined on the boundary. Got it? Okay, so for reasons I won't explain, Garber and I speculated that the way you should play this game is that each player would stake a non-random and shared between them fraction of her remaining fortune. And that would actually, if that's true, create a situation in which the relative fortunes of the players would remain constant throughout the game at the initial value. And it would have the effect that, in fact, Maxine would be winning each turn of the game with a constant probability lambda over 1 plus lambda, where lambda is the relative fortune Maxine to Mina at the beginning of the game. And then that would have the effect that the mean terminal receipt when players are playing well in this way would satisfy a biased version of the equation we saw before that's in green here at the bottom of the screen. if lambda is equal to 1, this is the equation we saw before. Otherwise, it's a biased version of the infinity Laplacian in this discrete setting. So yeah, Garber and I, about 4 years ago, started working on this. And in fact, we were joined by Yuji Fu, a graduate student at Berkeley, who made an important correction and development to what we did. So the 3-author paper now solves and realizes the speculation we had for a particular class of trees, for a particular class of graphs. So root reward trees are ones where you have a tree. That's not actually a tree that's drawn, but anyway, the boundary condition is that there's just a single one, and then everything else is 0. And it was also important to modify the game so it's an epsilon leisurely or lazy version, in which basically after stakes are made at a given turn, there's an independent coin that gets flipped. Probability of heads is epsilon, and the turn only takes place if it's heads. Otherwise, the monies are just swept away and no turn takes place. So with that variation, we proved that the hypothesis we had said was correct. And the shared stake proportion under that hypothesis, the players at any given situation stake the same amount. What is that amount? That's obviously a natural aspect of the problem. It's given here. It's kind of a ratio of a spatial derivative and a lambda derivative. It's a relationship between fighting for space up top on the right-hand side and worrying about money and worrying about the long term in the denominator downstairs in that formula at the bottom of the screen. Okay, so this is all to some extent just to give you a subjective history of the topic. State-governed tug-of-war that Garber and I had introduced. I say introduced, although there's a twist to that later on in the talk. We believe we'd introduced it. Okay, so while this research was going on, I decided to give things a bit of a twist and do a side project that developed into the Trails paper. Now, okay, so what's happening in the state-governed tug-of-war is that players are being forced to evaluate the positional importance of the game via the mechanism of staking. And that's something that is valuable and precious to them because stakes are limited by the initial amounts that players are given. These amounts are never being returned to them, neither during the game nor at the end. And so the original amount you have has to be budgeted throughout the game. You mustn't run out of it. So that's one way in which we made a resource precious, so gave the problem some meaning. But there's another way to make it resource precious, and that's to tell the players, as I say on the bottom of the slide, spend as much as you wish, but it has to be your own money. And in that way, we get back to there's no limited budgets in the Trail game from the beginning of this talk. You're spending, these players are considered to be, Mina and Maxine are wealthy. They don't worry about running out of money during the game. So they're using their money and doing the kind of linear optimization one sees in game theory without constraints. So that gets us back to the Trail game, and this is how I got to the Trail game and why I started studying it. Now, okay, and the third part of the talk, I want to simply tell you how the Trail game was solved. It was solved in a relatively explicit sense. Recall the two games. Finite or infinite trails with these boundary conditions. So a theorem addresses one of the three conceptual points I made at the end of the first part. For the infinite game played on Z, the space of time invariant Nash equilibria is in correspondence with solutions of the ABMN equations, which are a natural generalization of the equations that we saw. There's 4 equations for each site on Z for each integer. Now, if you take an ABMN equation solution and look at its AB components, that is that they parameterize, they are the space of solutions. They are the space of equilibria, time invariant Nash equilibria. The same is true for the finite game. Okay, so to tell you a little bit about then, taking now the point of departure to be the ABMN equations, I want to tell you a bit about how they were solved. So there is a derivative set of equations that basically any solution of the ABMN equations on Z leads to the MN component solving another set of equations that are on the screen here, in which we see capital M and capital N. That's the amount of skin you have in the game locally when you're at location I for the 2 players, and then there's some a pair of equations that are then solved by the components of the ABMN solution. So I want to tell you a little bit about the consequences of that for the space of solutions. So suppose at a given turn, the counter has reached some location, and suppose it's a situation where locally at the next turn, Maxine has just a little bit more to play for than Mina, which is to say that MI is just a little bit larger than NI. The mean amount that Maxine will win if she wins this turn minus what she'll win if she loses it, that difference is just a little bit larger for Maxine than it is for Mina. That's sort of represented by the picture at the bottom of the screen. Okay. Yeah. So then some simple transformations of the MN equations. Basically, I don't really expect you to absorb this in real time. Let's perhaps just look at the pictures at the bottom of the screen. They have the consequence that in the situation where MI is just a little bit higher than NI, you get this kind of outcome where MI, the mean, little MI, the mean amount you receive from location I, is that much closer to MI plus 1 than to MI minus 1. And that is also true for Mina's side of the story, but the effect is much more pronounced. So a small fraction of difference, MI pushed to the right in the penultimate picture, and in the bottom picture, the fraction and that rightward distance relative to the total is much smaller. That's the consequence of these equations. And then that allows us to introduce a quantity, take a given ABMN solution on Z, then I can define the central ratio, which is some representation of how much locally the players care about the game when the counter is at 0 in terms of the next move, roughly speaking. So the situation we have is one in which we can sort of compute the solution from the central ratio. There's only one parameter in describing the outcome, that was x, and so the central ratio is another way of parameterizing the outcomes. So the solution is rarely specified by the central ratio. And then what we see is that, I mean, the difference between M infinity, which is Maxine's terminal receipt in the event of victory, and M minus infinity, her defeat receipt, we divide up that interval between into by countably many points, which are all the provisional mean receipts at all the intermediate versus this is a monotone situation, and likewise for Mina, but the other way round. And then what we see is that we have a relatively big gap somewhere in the middle, but as we move away from there, there's rapid clustering of these points. But it's even more rapid when you move in the other direction, in the direction where you're provisionally losing. It's an even more rapid clustering. Okay, so to say that with some equations, to some extent, there's a relatively explicit, this is a quasi-rational function, a rational function with a square root involved, S, okay, I just think of S as being some relatively concrete function, given. Phi I rather, represents how much skin in the game there is locally at the next step for when it's at location I. And then there is this nice dynamical setup. When I have an ABMN solution, it's in fact the case that if I want to get from this relative ratio at location I to I plus 1, I do that by applying the map S as represented by the proposition at the bottom of this screen. So we have this sort of nice sort of dynamical structure. Let's look at the forward and backward orbits of this map S. They come in very rapidly towards 0, from 3 to 1/3, rapidly down to 0 at a doubly exponential rate. And when you take the inverse exists, it rises in a doubly exponential fashion, as you see. Okay? So, okay, here's an important quantity for the analysis that was done, the mean and margin map. Again, I have an ABMN solution on Z with its central ratio, this sort of local skin in the game relative incentive quantity for turn 1 if the game begins at 0. And then I can introduce a global counterpart to that. The Mina's relative incentive, MRI, is the kind of quantity I was talking about in incentive inch outcome mile. How much does one player care about the game relative to the other in terms of the overall outcome? You see, you've got the infinities involved, the terminal receipts involved there. So the mean and margin map is quite simple. It maps local to global. It maps the central ratio to Mina's relative incentive. There's a certain amount to take in here, perhaps difficult to absorb everything. Basically, though, we have a one-parameter family of boundary conditions specified by mean as winning receipt, or here, in fact, by the central ratio. That is the argument of this function, the mean and margin map. And that maps to the global relative incentive. So the range of this map is, in fact, the range of possible relative incentives that would give rise to Nash equilibrium. We'll see more about this. Okay, so there's a relatively explicit form for the mean and margin map that I won't inflict on you, but we have infinite sums of terms, each of which is a finite product of expressions that involve iterates of S and 2 or 3 other simple explicit functions. It's at this degree that we have. And these are kind of limits of expressions that you would get from finite trail games. Yeah, so indeed, if we look at the finite trail margin map, the analog of this for the finite trail game, so they're played with the boundary point being minus L and plus K, then I can also define a central ratio, relative skin in the game turns 0 when it begins at 0, mapping to the overall relative incentives in the game in terms of terminal receipts, the same kind of map. So, okay, I was thinking the M, these are the finite analogs. If I take K to L to infinity, I was thinking I should approximate the mean and margin map. So I started plotting MLK for some very finite values of MK and L. And I began to see a very striking picture develop very quickly, really, that for very small values here, really, 2 up to 4, 3, and you see a rather rapid convergence towards a function that's clearly going to be identically equal to 1. That seems to be the lesson of this. Even M43, a trail game of length 7, it seems that the mean and margin map is converging to a function that's identically equal to 1, something that has various consequences. But anyway, that's what I appear to be seeing. So let's get back and explore what the consequence of that would be for incentive inch outcome mile. So yeah, given that these functions seem to be converging to 1, it means that, in fact, if you had any incentive whatsoever that's different from 1 for Mina, suppose it has an incentive just a tiny, tiny bit bigger than 1, it would seem that it's not possible to achieve that relative incentive for an ABMN equation, because the image under this map, that is the space of possible relative incentives in terms of terminal receipts for the 2 players that can arise under Nash equilibrium. So if script M, the mean and margin map, is identically equal to 1, it means incentive inch outcome mile must be true in the strong sense that if X is bigger than 1, everything said in some sense is true, and the equilibria don't actually exist. Okay, but then I started to plot these functions a bit more carefully, and actually I realized something else was going on. These are the same functions being plotted, but in a more sensitive way, changing the vertical scale with a suitable vertical dilation. Note that the vertical dilation is shifting, and it is already becoming fairly fine in the lower left sketch of a trail of length 7. I'm plotting on a scale of 10 to the minus 4, I think, there. And I'm beginning to see this interesting kind of wiggle develop, where perhaps each time an extra wiggle appears, and it's not perhaps that obvious that that is converging to 1 anymore. Okay, so for a broader as well as a finer view of the finite mean and margin maps, okay, change of coordinates to some extent. The map S that is being used and related to the definition of the mean and margin map, it had these very rapidly converging or diverging forward and backward orbits. I want to just do a change of coordinates to get to a situation where basically applying S means going to the left by 1 on the real line, the kind of scaling you see here for new coordinates. So then I started replotting these functions for somewhat higher values, going up to trails of length 12. Here are 5 or 6 sketches. And over on the right, you see a version in which I have, in a completely artificial way, displaced these curves, just so you can see them, because they start overlapping with one another. So just to avoid that and to see the individual curves, I've displaced them somewhat. So then you have this rather clearer picture that each time you add an index, you get an extra little wiggle in this picture, and it's not really converging to 1, in fact. So the finer appraisal we have is that basically in transformed units, coordinates, the mean and margin map is in fact converging to a function, it would seem, that has this rather special specific behavior in which it's not converging identically to one, but rather to some more or less periodic function in these suitably scaled transformed units, in which the vertical, anyway, the range of the map is sitting on a scale of 10 to the minus 4, about the point 1. So incentive inch outcome mile, what do we learn about this from, if we can prove that? So quantified, in other words, the set of values that we can assign as mean as winning margin when Maxine's is 1, that's the standardization we have, if that's called X, then in order that one has a time invariant Nash equilibrium, X has to in fact lie in the range of the mean and margin map, because the mean and margin map is describing all of the equilibria essentially. And so what we seem to have now is evidence that the range is this very short interval 10 to the minus 4 about the symmetric point 1. So in other words, we seem to have a conclusion that if you have a very small amount, figuratively an inch of relative incentive for one player, and we just push above the right-hand end of this interval, that is enough to disrupt the existence of equilibrium. And it results in some sense in a mile, you know, the dollar involved here can assuredly go to the winning player, a mile of outcome for the more incentivized player. There is a complication actually that when one leaves this interval, there aren't any equilibria, and it becomes impossible to say how to actually play the game according to mathematical theory. So the notion that the more incentivized player is clearly winning is in fact a little bit mathematically questionable. But anyway, that's in some sense a side remark. So incentive inch outcome mile and this 10 to the minus 4 quantification of what that means. And then I thought, well, wait a minute, why don't I just check how many inches there are in a mile? And the answer is 63,000, which is in fact of the scale of 10 to the 4. So I'm using the phrase incentive inch outcome mile is actually to a remarkable extent quantitatively predictive of what happens in the problem in the relationship between inch and mile. Okay, so all right, let's actually get to the results. I mean, this is, I've been explaining the kinds of simulations I did and the things I was starting to believe were true, but what are the actual results that were obtained? So the main theorem in the Trail's paper concerns the infinite trail game played on Z with these boundary conditions I've been mentioned. So time invariant Nash equilibria indeed exist if and only if X belongs to an interval that takes the form of a closed interval lambda to 1 over lambda, where lambda is some value that is between 0 and 1. So this is what was rigorously proved. I got lambda away from 1 by this 10 to the minus 4 amount rigorously, and I conjectured that it's, in fact, the complementary bound is essentially true, that lambda is essentially 1 minus something of order 10 to the minus 4. Now, that is something that, in terms of my proof technique, would require computer assistance. And along with some nice monotonicities that they noted, two Berkeley students, Neo Lee and Adam Ostorovich, are proving that conjecture, in fact, which is a nice result to get because it rarely establishes rigorously that this rather striking behavior of sensitivity in which there is a non-degenerate scale of 10 to the minus 4 that's kind of canonically associated to this, in some sense, relatively simple problem, as quantification of incentive inch outcome mile is being proved in that sense. Okay, so then if I then take X in the sweet spot range, any time equilibrium there corresponds to an ABMN solution. And as such, we can talk about how the time invariant Nash equilibria behave. We have this notion, in fact, of the battlefield vertex. There are countably many time invariant Nash equilibria for a given value of X in this range. There's two equivalence classes of them under shifts of Z. Anyway, if we just focus on what one of these solutions look like, there is this battlefield vertex where players are staking pretty big. It's something like 15 cents they're prepared to stake or something like that In a game that, or maybe 10 cents it is, in a game where they're only going to get $1 and where there are infinitely many turns. So it's quite a lot to stake. And then you have the kind of asymmetric decay, rapid decay away from that, which I quantified rather precisely. So staking in the middle, it's between a dime and oh, I've forgotten the word for it. Oh, there isn't a word for it. Between 10 and 20 cents. I was going to say a nickel and a dime, but that's not correct. Anyway, they're staking between 10 and 20 cents in the middle. And then there's this precise description with this doubly exponential decay rates that are asymmetric and more rapid for the losing player. Okay, so then let's look at some interesting results, I think, about finite trail games. If we look at the symmetric game, where x is 1, just for definiteness, that has more than one Nash equilibrium in the sense we've been talking about, if and only if the game board has length at least 6. So if we look at the game board of length 6, in which 5 vertices you see are in open play, then there are 3 Nash equilibria, in fact. So the symmetric one that I identified earlier on in the talk, or the equations for it I did, that was how the route into the topic for me, that I think is somehow represented by the middle in this picture, with the stakes in the middle left picture and the mean terminal receipts to the various vertices on the right. And then there is a flip symmetry between the pictures up top and down bottom with asymmetric solutions, yeah, so in which one or other player is being advantaged, in fact. It corresponds to shifting the location in some sense of the battlefield vertex. In general, if you have a long finite interval, there are 2 to the number of vertices minus something like 6 or 7 Nash equilibrium, and then there are different possible locations of the where the battlefield is. So briefly, I don't have much time. Just really, I've got 2 parts of my talk, but I'm just going to go through them rather quickly because there is a rather remarkable alternative perspective that I was totally unaware of in conducting this research that I now want to capture something of. In 1987, Harris and Vickers, 2 now very prominent British economists, released an article called Racing with Uncertainty, in which a competition was happening between 2 firms to secure a patent by kind of getting technological advantage along the way. But the game they basically had, which was a counter moving to the left or right, is highly similar to the finite trail game. So this was back in the mid-late 80s. They called their model tug-of-war, nothing other than the same name. Their work generated 600 or so citations, economics, CS, and it's dominated by things like symmetric solutions and some of the considerations we've seen. Decisive early rounds, a discouragement effect. There have also been experimental studies. And then Parry, Schramm, Sheffield and Wilson that I've mentioned, tug-of-war from them, their PDE work, a comparable number of citations, the interest in PDE and probability. These bubbles are disjoint. That was really, I checked on Google Scholar, there was no article before us that cited both of them. So 500 each, and neither for both. So the 2 literatures of tug-of-war developed independently, sailing ships in the night, unaware of one another, with even the very name of the game, tug-of-war, being selected independently by the mathematicians at the later date. So, okay, so a caricature of the 2 strands is basically more complicated rules for deciding who wins in the economics on the left, and rather simple geometric settings on the right, with Parry, Schramm, Sheffield, Wilson, a fair or just bias coin, relatively trivial decision rules, but a richer geometric setting with connections to PDE via small step size in Euclidean domains. And finally, I just want to moot the possibility in my very short final section of the talk, state-governed tug-of-war and the Trail of Lost Pennies might be studied in richer geometric settings where we move to perhaps Euclidean settings, small step sizes. And in that way, the geometric richness of the mathematical literature and the complexity and delicacy of the decision rules seen in the economics literature could be unified in a way that would be mathematically satisfying and perhaps also of interest for applications in certain regards. Yeah, and I just end with an image of rapprochement between our two blades. That's it.
Thank you very much, Alan. That was very nice. Are there questions?
Yeah, I was wondering if you had a clear idea of well, why these oscillations appears, and is if there is a specific reason why they are so small in amplitude, and perhaps if like you can find a modification of the game or of the setup where the same oscillations would appear but being of macroscopic order instead of 10 to the minus 4.
Yeah, thanks. Right, so the oscillations were found by something that could be broadly speaking called exact solutions. I mean, the kinds of functions S you saw in the kinds of infinite products of things involving S and the ratio of them, these are in the broad category of explicit solutions. So in that sense, I was surprised to see this kind of behavior and this kind of outcome. But in a certain sense, in an interesting way, it reflects a theme that's very developed in economics of discouragement effect. And the only answer I can give in terms of intuition more relies on game theoretic or economic, well, things seen in the economics literature, like a game theoretic point of view, that at some level it seems that the kinds of intuition manifested by incentive inch outcome mile are kind of valid, but interestingly, they're also invalid. I mean, they restrict the length of this interval to be 10 to the minus 4 in this case, but they don't bring it down to be a singleton. So in terms of whether one could have, okay, is the 10 to the minus 4 in its precise value, this quantity, lambda minus 1, or in its scale, something that is more universal? That speaks to your second question. You expressed it in a negative form. I suppose, can one find setups where it becomes more macroscopic? If you want me to make wild speculation about that, my guess would be that no, maybe not, and that there is, or maybe, to be vague, in more or less natural settings, if you want me to wildly speculate, I would say that I wonder whether it could be the case that the quantity when you move to planar graphs, when you move to more general graphs, could remain relatively close to that kind of level. The students, Adam and Neo, another thing they did that was quite fun was to start simulating the ABMN equations, which have a natural analog in things like planar setups. And I was asking them, are there battlefield curves that correspond to battlefield vertices? What goes on with, well, kind of question you asked. And they did seem to provide some support for the conclusion that there's a variety of battlefield curves in a more general setup. And as you move lambda away from 1 by a significant amount, things collapse to the boundary. I think simulations do support that to some extent. Whether, of course, mathematically one could come up with some example of something a bit different and have macroscopic difference, I don't know. But the general vein of answer I want to give is that it does make, in some complicated way, some intuitive sense, although it's very hard to pin down the exact scale via intuition, of course. And my speculation would be that there is something at least a little bit universal, or at least generalizable, about something about that smallness, which I think is something I'm motivated to broadcast and to think about further, because I think it's a really quite fun and intriguing aspect, to me at least, that you have this 10 to the minus 4 that really sits there and it doesn't go to 0. It is a genuine quantity. And the question of whether it's a little bit universal or generalizable is something that's, I think, an intriguing prospect.
Is there another question? Well, if it's not the case, maybe we proceed to thank Alan for this very nice talk.